Good afternoon, students. Today we will be discussing Unit 2 of your course Numerical Methods, and your Unit 2 consists of interpolation. Okay, so these are your recommended textbooks. As you all know, and these are few of your reference books which you can follow. Now, what we will be discussing today, we will be discussing about interpolation. So, basically what is interpolation we will be discussing, then we will be discussing about the types of interpolation, and then we will be discussing polynomial interpolation, okay, out of which we will be discussing Lagrange and Newton's interpolation. So, before going to what is interpolation, let's have a look at this population survey. Okay, so here you can see from 1941 to 2011 population survey had been done. As you can see from here the PDF, the population survey is conducted every 10 years gap. Obviously we all know it's quite expensive to conduct every year, so it's conducted in a interval like 10 years gap, 12 years gap, it's conducted. Okay. Now from this one, if I ask you that what will be the population size in 2010, so what will be your answer? Or if I ask you what will be the population in the year 2025, so what will be your answer? See, we can at least for this class we will be omitting the question that what would be the size in 2025, because we will be, in that case we will be predicting the future. So, and that comes under the category of extrapolation. So, we can, for this class we can omit this question. But if I come back to this question that what will be the population size in 2010, so what will be your answer? Now see, from the population the graph, 2010 is not mentioned anywhere. Also, if you want to predict, if you want to say what is the population size in 2010, you need mathematical models. But for mathematical model, to implement mathematical model, there are many constraints like you can say like population immigration, population migration, competition, natural disasters, and there will be various constraints. So, formulating a mathematical model, a realistic mathematical model, it is not that much the easier task. So, what will be the answer if I simply want to know the population size in 2010? Now, okay, now let's move to another example. So, as you can see, here is the data analysis for the case of epidemic. Okay, so here also the time is given in weeks and the people died. These are the data. So, if I want to ask, if I want to know what will be the number of people who died in first week, what will be your answer? So, here also if we like use a mathematical model, there will be many constraints since it is a case of epidemic. So, there will be many constraints and it will not be an easier task. So, how can you say what will be the number of people who died in first week? So, what will be your answer, or what will be the way you want to give the answer? Okay. Now, let's move to our third problem. So, here you can see this is a function. Okay, you can see it's a very cumbersome function. There are many terms, there are transcendental terms involved. Obviously, there are terms like polynomial terms are involved, but mostly you can see transcendental terms are also involved. So, if I want to find the differentiation of this function, what will be your answer? Or if I want to find the integration of this function, what will be your answer? See, finding integration or differentiation of such a cumbersome function, it's a tough task. Okay, it's a tough task. So, what we can do? So, is there any way? So, yes, one way is there if we can replace this function by a more simpler function who will be following the exact behavior as this function. This is one of the way we can make the task easier. Instead of this cumbersome function, suppose we are finding a more simplistic, let's say a polynomial function which is having the same behavior as this. Then your task is easier, it will become easier. You can differentiate it, you can integrate it, or anyways you can evaluate this term also, whatsoever is the task given to you. So, that way your task will be easier, isn't it? So, even here also in our first example also, here the population survey also, here if instead of finding one complicated mathematical model with many constraints which is not too realistic, if we can find a simpler function which satisfies all these data points, then our task of finding the population in the year 2010, it will be an easier task for you. Similarly, for your epidemic model also, it will be an easier task if you can find some simplistic function. So the form of the function, it can be a polynomial function, it can be sine function, trigonometric function, logarithm function, that we will be discussing later, but the task will be easier, isn't it? So now we can go to the definition of interpolation. Now after all this example, it is clear to you. So what is interpolation? So to overcome the difficulties, above difficulties, we look for a suitable function which will serve our purpose. And the process is called interpolation. So what is interpolation? If I ask you, interpolation is a process by which we can develop a function from a discrete set of data points. Okay? So in our previous examples, the discrete points will be the population, the census years which were taken. So that will be our discrete data points. And the obtained function, the simpler function which we call, so that obtained function will be the interpolating function or interpolant. So instead of discrete data, if we are given a function, then from that function we can generate the data points we require, and then we can compute the functional values. So what are our purposes of, so you need to know the purposes of interpolation. So what are our purposes of interpolation? So our purpose first is plotting a smooth graph through discrete data points. Next is quick and easy evolution of a mathematical function. Third one, as we have, that is the main motive, we are replacing a difficult function by an easy one. So that is our main objective, isn't it? And reading between the lines of a table. Means what? Like in the first example you have seen, we are reading between the lines. We are finding the population in 2010, which was not given in the data. And say, after that, the last one is differentiating or integrating tabular data. So these are your purposes. Now, as I have told you that the function, the difficult function can be replaced with an easy one, easy function. So what will be the form of that easy function? So that form of an easy function can be a polynomial, the form of the easy function can be a trigonometric function or exponential function or rational function. So or any function. So basically there are many types of interpolation based on the easier function which you choose. So first will be our polynomial interpolation, then interpolation with trigonometric functions, interpolation with exponential functions, and interpolation with rational functions. So these are some among the many types of interpolating functions. But since in this course we are constrained only to talk about polynomial interpolation. Okay, so today we will be discussing about polynomial interpolation. Now generally there are two types of polynomial interpolation which we will be discussing: Lagrange interpolation and Newton's interpolation. So we will focus only on these two among many. Okay, in our course we will be focusing only on these two. Now say, what is Lagrange interpolation? Before starting, before giving you the formula for Lagrange interpolation, what is our requirement? What is our basic requirement? We require discrete data points. So we are given a set of data points. Suppose these are the set of data points we are given. Okay. Now I am giving you directly the formula. So what is our aim? So what is our aim? Our aim is to construct a function which satisfies this data point, isn't it? Then with keeping this aim in mind, I am giving you the Lagrange interpolating polynomial which is of this form, as you can see in the screen. So this is your Lagrange interpolating polynomial. Okay. So here as you can see, LJT, this have a separate name which is known as Lagrange basis. Okay, and it have this special property. So as you can see in the screen, it has this special property. The derivation of Lagrange polynomial we can do in next class, but for today's class we will be giving only the formula, and which is this one. This is the formula. Now this is one of the example for Lagrange, for finding a polynomial using Lagrange interpolation. So this example you can keep, you can note down. Now next coming to Newton's interpolation. So here also what is the first basic requirements we need? We need data sets, isn't it? So we are given data points. These are the data points we are given. Then with this data point, Newton's interpolating polynomial is of this form. This is the form, okay. The derivation we can keep for our next class. So this is the form of the Newton's interpolating polynomial. Now here what are this, isn't it? F t naught, comma t1, what are these? So these are nothing but these have the following values. Actually these things, it can be written more simpler way in a divided difference table, which will be clear when we move to our example. So this is your example. So here the example is we have to find the Newton form of the interpolating polynomial using the given data set, okay. So as mentioned here, the values, isn't it? F t i's, F t naught, t1, all these values. So it can be written more simplistically in a divided difference table. This is your divided difference table. You can write it more systematically here, and using these values, the Newton's polynomial is obtained, okay. So with this, so what we have learned today, we have learned about the Newton's interpolating polynomial and the Lagrange interpolating polynomial. Okay, thank you.